How the internet actually works. Imagine waking up tomorrow morning. You pick up your phone, you open YouTube, you tap on a video, and within seconds, a video recorded somewhere on the other side of the planet appears on your screen. No wires running from your phone to the creator's house, no satellite beam traveling directly into your bedroom, no humans sitting somewhere manually sending the video to you. You simply tap, and somehow, the internet finds a way. But here's the question almost nobody stops to ask. How? How can a message sent from a phone in your bedroom travel across cities, countries, oceans, and thousands of computers and arrive at exactly the right device in just a few seconds? How does your phone know where YouTube is? How does YouTube know where you are? How does a video get divided into tiny pieces, travel through completely different routes, cross the ocean, and somehow become a perfect video again on your screen? And perhaps the most fascinating question of all, who actually controls the internet? Because the internet isn't one giant machine. There is no single building called the internet. There is no master computer sitting somewhere in the world controlling every website. The internet is something far stranger. It is a gigantic network of networks, billions of devices, millions of servers, thousands of data centers, massive fiber-optic cables crossing oceans, cell towers, routers, undersea cables, satellites, and invisible systems working together every second. And most of the time, you never see any of it. You simply tap a screen, and the world responds. But behind that simple tap is one of the most extraordinary technological systems humanity has ever built. Today, we are going behind the screen. We are going to follow a single piece of information from the moment you press a button until it reaches your device. We will uncover what really happens when you type a website address, why websites have strange numerical addresses, how routers decide where information should go, why your data is broken into tiny packets, how those packets cross entire oceans, why sometimes your connection suddenly becomes slow, what DNS actually does, what an IP address really means, what happens inside a data center, how Wi-Fi is connected to the global internet, and why the internet can continue functioning even when individual networks fail. By the end of this video, you will never look at that little Wi-Fi symbol on your phone the same way again. Welcome to Behind the Story. Let's begin. Chapter 1. The internet doesn't exist in one place. The first mistake people make when imagining the internet is thinking of it as a single thing. We say, the internet is down, the internet is fast, the internet is slow, the internet is working. But technically, there is no single machine called the internet. The internet is a network of networks. That sentence sounds simple, but it changes everything. Your home network is one network. Your mobile carrier operates another. Your university has another. A company has another. A cloud provider has another. A massive technology company may operate thousands of interconnected networks and data centers. These networks connect to other networks, which connect to even more networks, until they form a planetary system of communication. Imagine millions of islands. Each island has its own roads, but the islands are connected by bridges. Now imagine those islands are networks, and the bridges are connections between them. That is the basic idea behind the internet. Your phone doesn't need a direct connection to every website in the world. It only needs a connection to a network that can reach another network, which can reach another, and eventually reach the server you want. And that is why the internet is so powerful. It doesn't depend on one road. It depends on many roads. If one connection fails, traffic can sometimes be redirected through another. If one server becomes unavailable, another server may respond. If one data center experiences a problem, systems can sometimes move traffic somewhere else. This distributed design is one of the fundamental reasons the internet became so resilient. But now we have a problem. If there are billions of devices, how does one device know where another device is? If you want to send a letter, you need an address. The internet needs addresses too. And this brings us to one of the most important concepts in networking, the IP address. Chapter 2. Every device needs an address. Imagine a city with millions of houses, but none of them have addresses. You want to send a package? Where would you send it? You could write, "Send this to Muhammad." But which Muhammad? Which house? Which street? Which city? The internet faces exactly the same problem. There are billions of connected devices: computers, phones, servers, cameras, routers, smart TVs, cars, and countless other systems. They need a way to identify where information should go. That's where IP addresses come in. IP stands for Internet Protocol. An IP address is essentially a numerical address used for communication across an IP network. You may have seen something like 192.168.1.10. That looks like a random collection of numbers, but it represents an address within a network. And there are different kinds of IP addresses. Some are used inside private networks. Others identify systems across the public internet. There is also IPv6, the newer generation of Internet Protocol, designed to provide an enormous number of addresses. Why was IPv6 necessary? Because the world ran into a problem. There simply weren't enough IPv4 addresses to give every device its own unique public address forever. Humanity kept connecting more devices, more phones, more computers, more servers, more smart devices, more everything. So networking engineers developed IPv6, which provides an extraordinarily larger address space. But here's something interesting. When you open a website, you usually don't type an IP address. You type something like youtube.com, google.com, wikipedia.org. And this creates another question. How does the internet transform a name like YouTube into a numerical destination? The answer is one of the most important systems on the internet, DNS. Chapter 3, The Internet's Phone Book. Imagine you have someone's phone number, but you don't want to remember the number. You remember their name. So you open your contacts, search for their name, and your phone finds the number. DNS works in a similar way. DNS stands for Domain Name System. Its job is to translate human-friendly domain names into information that computers can use to locate services, because humans are much better at remembering names than long numerical addresses. Imagine if every time you wanted to watch a video, you had to type something like 142.250.something.something. You would hate the internet. Instead, you type a name. Your device asks, "Where is this domain?" And DNS helps answer that question. But even this process is more complicated than it appears. Your device may first check information it already knows. Perhaps the answer is stored in a local cache. If not, a DNS resolver may need to find the answer, and that resolver may communicate with other DNS servers. Eventually, the system can identify the appropriate address information. All of this can happen incredibly quickly. Often, you don't even notice it. You tap a website, DNS resolution occurs, and the next stage begins. Your device needs to establish communication with the destination. And this is where another fundamental concept enters the story: packets. Chapter 4. Your message is not one message. This is where the internet becomes truly fascinating. Suppose you want to send a huge file to someone, maybe a high-resolution photograph, maybe a video, maybe a document. It would be inefficient to treat the entire file as one gigantic block of information. Instead, network communication is generally divided into smaller units. These are commonly called packets. Think about sending a giant book through the mail. Instead of putting the entire book into one enormous package, you could divide it into many smaller boxes. Box 1, Box 2, Box 3, Box 4. Each box can travel through the delivery system. Some may take different routes. They may encounter different delays, but eventually the recipient can put everything back together. That's roughly the idea behind packet-based communication. Your video isn't simply one giant stream traveling as a single object from the server to your phone. Information is transmitted through networks using packets and other protocol mechanisms. Those packets contain information that helps networks know where they came from, where they're going, and how they should be handled. And here's where something remarkable happens. Different packets don't necessarily have to follow the exact same physical path. One packet may travel through one network, another may travel through another. A router looks at the destination information, consults its routing information, and makes a decision about where to send the packet next. That decision happens again, and again, and again, until the packet reaches its destination network. This is why routers are so important. Chapter 5. The traffic controllers of the internet. Imagine the world's largest city, with billions of cars moving simultaneously. Now imagine there are no traffic lights, no central traffic controller, and no single person who knows where every car is going. Instead, at every major intersection, there is an intelligent system that looks at the destination and decides which road makes the most sense. That is roughly what routers do. A router connects networks. Its job is to move traffic towards its destination. When information arrives, the router examines the destination information. Then it determines where to send the packet next. It doesn't need to know the entire journey in the same way a human driver might. It simply needs to make an appropriate next step decision. This creates something extraordinary. The internet doesn't require one giant central map controlling every packet. Instead, networks exchange routing information. Routers maintain routing information that allows them to make forwarding decisions. At the scale of the global internet, this becomes incredibly complex. Internet service providers exchange traffic. Large networks connect with other large networks. Organizations establish direct connections. Some networks are customers of other networks. Others exchange traffic between themselves. And all of this creates a constantly changing global web of connectivity. But there is still one massive obstacle. What if the server you want is thousands of kilometers away? What if it's on another continent? Your information needs to cross the ocean. And this leads us to one of the most remarkable pieces of infrastructure humans have ever built: undersea cables. Chapter 6. The secret highways under the ocean. When people imagine the internet, they often imagine satellites. They picture information flying through space, bouncing from satellites and coming back down somewhere else. Satellites do play important roles in communications, but much of the world's internet traffic travels through something far less glamorous: cables. And not just ordinary cables. Massive fiber-optic cables run across the floors of oceans. They connect continents. They connect countries. They form some of the most important physical infrastructure supporting global communications. And inside those cables, information travels as light. Think about that for a moment. You sit in your room. You open a website hosted thousands of kilometers away. You press a button, and information can travel through glass fibers as pulses of light, through cables lying on the ocean floor, before eventually reaching another continent. The concept sounds almost futuristic, but it's real. Fiber optic technology is one of the foundations of modern communications. Instead of sending information as electrical signals through traditional copper wires over long distances, fiber can transmit data using light. And because light can carry enormous amounts of information, fiber optic networks can support astonishing volumes of traffic. But those cables are not invincible. They can be damaged. Anchors can drag across the seabed, construction activities can cause damage, natural events can disrupt infrastructure. And when a major cable is damaged, the effects can sometimes reach far beyond the location of the physical break. Yet the internet has another advantage. There are often multiple paths. Traffic can sometimes be rerouted. And this is another reason the global internet doesn't collapse every time one cable fails. But where does all this information ultimately go? It goes to machines. Very powerful machines. Welcome to the data center. Chapter 7. Where the internet lives. If you imagine the internet as something floating invisibly in the air, forget that image. Inside these facilities, you can find enormous numbers of servers. Servers are computers designed to provide services to other computers. When you watch a video, when you load a website, when you send an email, when you save a file to the cloud, some server somewhere may be involved. And these aren't ordinary home computers. Large data centers contain racks filled with powerful machines. They require electricity, cooling, networking, security, backup systems, monitoring, physical protection, and carefully designed infrastructure. Because when millions of people depend on a service, even a small failure can become a major event. That's why large technology companies often operate multiple data centers across different geographic regions. Instead of putting everything in one building, they distribute systems. This can improve reliability, it can reduce latency, and it can help services continue operating when one location experiences problems. But now another question appears. If there are many servers, which one actually responds to you? The answer can depend on where you are, what service you're using, how the company's infrastructure is designed, and many other factors. A user in Asia may receive data from a nearby regional infrastructure location. A user in Europe may receive it from another. This is one reason modern websites can feel incredibly fast, despite the enormous distance between you and the company behind them. But distance still matters, and this brings us to latency. Chapter 8: Why the Internet Sometimes Feels Slow. Have you ever clicked a video and watched the loading circle spin? You stare at it, you wait, you refresh the page, you check your Wi-Fi, and you think, the internet is broken. But what does slow internet actually mean? There are several possibilities. Your connection might have limited bandwidth, your network might be congested, your Wi-Fi signal might be weak, the server might be overloaded, a network between you and the server might be experiencing congestion, there could be routing problems, or the delay may simply be caused by distance and the time required for information to travel. One important concept is latency. Latency is essentially the delay involved in communication. Imagine shouting to someone across a valley. You speak, the sound travels, they hear you, and then they respond. The time between those events is a kind of delay. Networks experience similar delays. The farther information has to travel, and the more network equipment it passes through, the more opportunities there are for delay. But bandwidth is different. Imagine a highway. Latency is similar to how long it takes one car to travel from one city to another. Bandwidth is closer to how many cars the highway can carry at once. A highway can be extremely wide, but a particular car still needs time to reach its destination, and a short road can become heavily congested. That's why a connection with a high advertised speed can still feel slow under certain conditions. The internet is not simply about speed. It's about an enormous combination of infrastructure, capacity, routing, congestion, processing, and distance. And there is another layer most people don't think about: the protocols. Chapter 9: The Rules That Make the Internet Work. Imagine millions of people trying to communicate, but everyone speaks a completely different language. One person sends a message. Another doesn't know how to interpret it. Someone else doesn't know how to respond. Chaos. For the internet to function, devices need shared rules. These rules are implemented through protocols. Protocols define how systems communicate. They establish formats, procedures, expectations, and behaviors. One of the most famous groups of protocols is TCP/IP. IP helps with addressing and routing. TCP can provide reliable, ordered delivery for applications that need those properties. That modern internet communication uses many protocols. For example, HTTP is fundamental to the web. HTTPS adds encryption through TLS. DNS handles domain name resolution, and many other protocols handle different layers and functions. The important thing to understand is this: the internet isn't held together by one magical technology. It's a stack. Different technologies solve different problems. One handles addressing, another handles routing, another handles reliable transport, another handles secure communication, another helps your browser communicate with a web server. Together, these layers create something that feels incredibly simple from the user's perspective. You open a browser, you type a name, you press enter, and a website appears. But underneath that single action, multiple systems may have already communicated. And then there is security, because without encryption, the internet would be a very different place. Chapter 10: What happens when you visit an HTTPS website? Let's imagine you type a secure website address into your browser. You press enter. Your device needs to communicate with the server. But how can you know that you're actually talking to the real website? And how can your information travel across networks without being readable by everyone who handles the traffic? This is where encryption and TLS become essential. HTTPS uses TLS to protect communications between your browser and the server. Instead of sending sensitive information as easily readable text, the communication is encrypted. Your browser and the server establish cryptographic parameters that allow them to communicate securely. The result is that someone observing the network traffic should not simply be able to read the contents of your encrypted communication. This doesn't mean the internet becomes magically anonymous. That's an important distinction. Encryption protects the contents of communication, but other information can still exist. For example, your device needs to communicate with a network. Servers need to receive connections. Systems may record logs. Websites can collect information through their own mechanisms. Your internet provider may see certain metadata about your connections. So encryption is powerful, but it isn't the same thing as invisibility. And this brings us to another misconception. When you connect to Wi-Fi, you are not directly connecting to the entire internet. You're connecting to a local network. Chapter 11, What Wi-Fi Actually Does. You walk into a room, you open your phone, you see the Wi-Fi symbol, you connect, and suddenly you have access to the internet. But Wi-Fi itself is not the internet. Wi-Fi is a wireless networking technology. It allows devices to communicate over radio waves with a wireless access point. That access point is typically connected to a router or another networking system. From there, your traffic can enter your home network, then your internet service provider's network, then larger networks, and eventually the global internet. So when you are sitting on your couch watching a video, your phone isn't magically talking directly to YouTube through the air. Your phone communicates wirelessly with your local access point. Your local network connects outward. Your ISP carries the traffic. Other networks carry it further. And eventually, the destination infrastructure responds. The process happens so quickly that your brain compresses all of those steps into one simple experience. I opened YouTube. But technically, you just triggered a global chain reaction involving machines and networks across potentially enormous distances. And that chain reaction doesn't stop with your video. Every time you scroll, you may trigger more network requests: images, advertisements, analytics, fonts, scripts, recommendations, comments, thumbnails. All of these components can involve additional communication between your device and servers. The modern web is not one document, it's an ecosystem, and that ecosystem is constantly talking. No single entity owns the internet. It is managed by a patchwork of private companies, governments, and standards organizations that cooperate to exchange traffic across borders. This architecture behaves like a living ecosystem. It grows and adapts as new data centers are built and new connections are established. This interconnectedness creates vulnerabilities. A routing error or a severed cable can cause a cascade, taking down unrelated services that share the underlying infrastructure. The cloud is a marketing term for this physical reality. Your data is not in the sky. It is stored on someone else's computer, inside a building, powered by a local grid. The decentralized nature of the network provides resilience, but its physical dependencies mean that local failures can have global consequences. When you type a URL and press enter, a DNS request leaves your phone, passes through your router, and travels through your ISP's network. It may cross an ocean via fiber-optic cables, guided by routers making micro-decisions at every intersection. A server receives the request, processes it, and breaks the response into packets for the return. These packets travel back through the same network web, reaching your home router, and finally crossing the room as radio waves to your device. This planetary chain reaction happens in milliseconds. The complexity is hidden behind a simple interface, allowing the user to focus on the result rather than the machine. The internet is becoming the core infrastructure for the physical world. Factories, medical devices, and entire cities are being integrated into this network. A system built to connect people has become a critical dependency. Our economies, hospitals, and governments now rely on these connections to function. Beneath the glass of the screen lies a massive physical machine wrapped around the planet, a system capable of moving information across oceans in fractions of a second. We click, we scroll, and we watch, while the machine beneath our fingertips keeps moving.